Have you ever imagined trains that float in midair? Deep within the mountains of Japan lies one of the world's most extraordinary technological achievements, a 43-kilometer magnetic levitation train track. This engineering marvel will eventually form part of the world's first intercity maglev system, connecting Tokyo and Osaka at breathtaking speeds of 500 kilometers per hour. Using superconducting magnets, these trains hover a mere 10 centimeters above the track, eliminating friction and allowing for unprecedented velocity. What makes these trains truly revolutionary is their ability to operate in virtually any weather condition. With no physical contact with the track, maintenance costs plummet, while reliability soars. Yet despite these remarkable advantages, high-speed maglev systems remain exceedingly rare globally. The contrast is striking: just 400 kilometers of maglev tracks exist worldwide, compared to 60,000 kilometers of conventional high-speed rail already in operation, with another 50,000 kilometers under construction. The science of levitation. How exactly do you make a 700-passenger train float above the ground? There are two primary approaches to magnetic levitation: pulling the train upward using attractive forces, or pushing it upward with repulsive forces. Shanghai's 30-kilometer maglev line uses electromagnetic suspension, where electromagnets pull the train toward a magnetic rail, maintaining a precise gap of 8 to 12 millimeters. This active system requires constant adjustments through feedback loops. Japan chose a different path with their LO series trains, using electrodynamic suspension. This system creates a significantly larger 10-centimeter gap, crucial in earthquake-prone regions. Magnets on board the train interact with passive coils embedded in the guideway, generating opposing magnetic fields. When the train moves over these coils at speed, the changing magnetic field induces currents that lift the train. This elegant solution is passively stable. If the train drifts from center, naturally occurring forces push it back into position. Superconducting superiority. What truly sets the Japanese maglev apart is its use of superconducting magnets. These remarkable components generate magnetic fields powerful enough to levitate an entire train while consuming zero electrical resistance. The niobium titanium coils must remain below their critical temperature, requiring sophisticated cooling systems utilizing liquid helium and nitrogen. Each train car contains 8 of these superconducting coils, 4 on each side. The cooling system employs pulse tube refrigerators, the same technology used in the James Webb Space Telescope. These ingenious devices use sound waves to create temperature differentials. Inside a closed tube, a standing sound wave generates areas of compression with high pressure and temperature. Heat exchangers transfer this thermal energy away from the superconducting coils, maintaining their critical temperature. This seemingly simple principle enables some of the most advanced transportation technology on Earth. Magnetic challenges with such powerful magnetic fields present. How do engineers protect passengers from their effects? Superconducting magnets generate field strengths that could wreak havoc on electronic devices and potentially affect health. The solution lies in careful magnetic field management using principles of reluctance. The magnetic equivalent of electrical resistance. Specially designed electric steel shielding containing 3% silicon diverts the magnetic field away from passenger cabins. Engineers further refine this protection through careful magnet arrangement. By positioning coils with alternating polarities on each side of the train, they create a bubble of minimal magnetic field strength through the corridors. The resulting field inside the cabin measures just 0.5 millitesla, comparable to Earth's natural magnetic field. This elegant design solution enables passengers to travel safely at unprecedented speeds without experiencing the powerful magnetic forces that make their journey possible. Propulsion and power without wheels, making contact with the ground. How does a levitating train move forward? The answer lies in linear motors, essentially conventional electric motors unwrapped and laid flat along the guideway. These motors use precisely timed electromagnetic pulses to push and pull the train along its path. When braking, this system works in reverse through regenerative braking, capturing kinetic energy and converting it back to electricity. Powering these massive machines presents another engineering challenge. Early prototypes used onboard gas turbines, but modern systems employ linear induction coils that collect power from the changing magnetic fields in the guideway itself. While this creates some magnetic drag, it's far more efficient than carrying heavy generators on board. The system's design allows for seamless acceleration and deceleration without the mechanical limitations of traditional wheel-rail interfaces, enabling those remarkable 500 km per hour speeds. Japan's magnetic vision. Why has Japan invested so heavily in this futuristic technology? The journey began immediately after they launched the world's first high-speed train, the Shinkansen, in 1964. Engineers were already dreaming of reducing the Tokyo-Osaka journey from 4 hours to under 1 hour. By the 1970s, testing was underway on short tracks in Miyazaki, with early prototypes reaching modest speeds of 60 km per hour, but progress accelerated rapidly by 1995. Test vehicles achieved 411 km per hour. The Yamanashi test track, constructed along the future Tokyo-Nagoya route, transformed these prototypes into a practical transportation system. Today's LO series trains can carry 700 passengers at 500 km per hour, promising to revolutionize domestic travel in Japan. The first phase of the commercial line, spanning 285 kilometers between Tokyo and Nagoya, is scheduled to open by 2027. The full 438-kilometer extension to Osaka should follow a decade later, culminating a journey of technological development spanning over half a century. The economic reality: despite their technological brilliance, high-speed maglev systems face significant economic challenges. The Tokyo-Nagoya section recently saw cost estimates rise to $13.7 billion, approximately $77 million per kilometer. This makes maglev systems between 10 and 50 times more expensive than conventional high-speed rail. The French TGV network, built in the 1980s and 1990s, cost just $2 million per kilometer by comparison. The economics of transportation modes create natural sweet spots for different technologies. For cities 200 to 800 kilometers apart, high-speed rail typically outperforms both cars and planes when considering total journey time. Maglev's primary advantage is extending this competitive range by decreasing travel times. The future of floating travel: will we ever see magnetic levitation trains connecting cities around the world? For now, the radical cost increases over conventional high-speed rail make widespread adoption unlikely. Even in regions perfectly suited for rail transportation like the Texas Triangle with its 4 major population centers, conventional rail projects struggle to gain traction against entrenched highway and airline interests. The economics simply don't compute for most applications. But technological breakthroughs could change this equation. Recent speculation about room temperature superconductors has renewed interest in magnetic levitation technologies. If such materials become commercially viable, they could dramatically reduce the complexity and cost of maglev systems. What seems financially impractical today could become tomorrow's transportation revolution. If you've enjoyed exploring the fascinating world of magnetic levitation with us, please subscribe to Mindcrafted for more deep dives into cutting-edge technologies. Share your thoughts in the comments. Would you ride a 500 km per hour floating train if you had the chance?